Okay, question 4. The unit of potential difference is the volt. Use the equation W equals QV to show that the volt may be written in base units as kilograms meters squared, amps to the -1, seconds to the -3. Okay, so let's make a little look with that then. So W equals QV, or VQ. What that's telling us is the work done is V over Q. So let's see what potential difference is. So that's W over Q. Now if we look at the units, that's going to tell me that the volt is going to equal a joule per coulomb. So now we need to know what the defining equations are for joule, which is work done, and we know that work done should be a force multiplied by a distance moved in the direction of the force, and the amount of charge delivered is equal to the current multiplied by the time. Now, if we look at these two equations, that's a base unit, or base quantity. Sorry, I'll put that as amps. That should be current as an I. Current is a base unit and time is a base unit, but force isn't, so we need to know that force is technically the rate of change of momentum. But for the sake of this, we'll do it as mass times acceleration, and acceleration is not a base quantity, mass is, so acceleration is the rate of change of velocity, and velocity isn't, so velocity is the rate of change of displacement. So base quantity, we can now work it out. So if we have a look, hopefully you already realise that acceleration is meters seconds to the -2. Mass, so the Newton is going to be kilograms meters seconds to the -2, and therefore the joule is the force times by the distance, so the joule is going to be kilograms meters squared seconds to the -2. And if we look at the coulomb, that's going to give me, that's going to be amp seconds. Okay, and we want joules per coulomb, so that's going to be joules, which is kilograms meters squared seconds to the -2, and divided by the coulomb, which will be amps to the -1, seconds to the -1. And if we combine all of that lot together, we're going to get to the kilogram meter squared amp to the -1, seconds to the -3, which is what they're after. So let's move on. On to part B. The student is investigating a potential divider circuit containing a light-dependent resistor, LDR. The student sets up the circuit as shown in figure 4. The battery has an EMF of 6 volts and negligible internal resistance. The resistor has a resistance of 1.2 kiloohms. In a dark room, the voltmeter reading is 5.1 volts. So we've got to show that the resistance of the LDR is 6,800 ohms. Okay, so what we'll need to do is, to begin with, is we know so it's got 5.1 volts across it. If we knew how much current was going through it, because resistance is V over I, then we're there. So if we've got 5.1 volts here, I can work out I must have 0.9 volts across the 1.2k resistor, and therefore the current flowing through that resistor is going to be the same as the current flowing through the LDR. So that current is going to be V over R, which will be 1.2 times 10 to the 3 over, got that the wrong way around, 0.9 over 1.2 times 10 to the 3. Now I know the current and I know the the potential difference here, so therefore the resistance of the LDR is going to be 5.1, potential difference across it, divided by the current, which will be 1.2 times 10 to the 3 over 0.9, and that should come out as being exactly 6,800 ohms. That's part one. Now on to part two. We've now got to calculate the current delivered by the battery. Oh, I've just done that. I might stop this and start again.
Leave that in.
They're obviously trying to get you to do it a different way. Sod it. It's 0.9 over 1.2 times 10 to the 3. Which is 7.5 times 10 to the minus 4 amps. Just goes to show there's more than one way to skin a cat. Right, part C. The circuit is moved so that the LDR is now in sunlight. Without reference to the potential divider equation, describe and explain how the readings on the ammeter and the voltmeter will change. Okay, so first thing you need to realize is the resistance of the LDR will decrease when we put it into light. So the total, oh, what happened there? Back a page. Total resistance decreases, and if the total resistance decreases, the current will increase. So that's going to increase the reading on the ammeter, and if the current increases, the potential difference across the resistor will increase. So if we've got now, because we've got a larger current, let's just explain that point a bit more, we've got a larger current flowing through both because the total resistance is decreased. This is a fixed resistor, so with a larger current flowing through it, it will have a greater PD across it. So that will mean, because I've got a greater potential difference across here, well, the potential difference across this plus this potential difference must add up to 6. That would mean the voltmeter reading will go down.